In the quiet Bavarian city of Würzburg, Germany, on December 5, 1901, a child was born who would one day redefine humanity's understanding of reality itself. His name was Werner Karl Heisenberg. From the moment his small hands began to turn the pages of his father's old Greek and Latin texts, there was an unusual spark in his eyes, a hunger to understand not merely the surface of things but the hidden forces that governed them. The turn of the century was an age of change. Empires stood tall, electricity was weaving its way into everyday life, and the world was still ruled by the comforting certainty of Newtonian physics. But beneath the calm surface of this scientific confidence, new questions were beginning to tremble. Questions that would one day shake the foundation of human knowledge. Heisenberg would grow up to be the one who faced those questions head-on. His father, Dr. August Heisenberg, was a scholar of Greek philology at the University of Munich, a man of deep intellect and classical discipline. His mother, Annie Wecklin, came from a family steeped in education. Her father had been the headmaster of a prestigious gymnasium. The Heisenberg home was filled with books, debate, and music. The rhythm of the household was academic. Discussions of philosophy and language at the dinner table, the sound of piano keys echoing through the hallways in the evenings. Young Werner absorbed it all with a quiet intensity. The intellectual air of his home shaped him, but his curiosity extended far beyond books. He was drawn to the natural world, to patterns of light on the water, to the strange stillness of the stars. Even as a boy, he saw the world not as a series of isolated things, but as a network of relationships waiting to be understood. The Germany of Heisenberg's youth was a country striding into modernity. Industrial progress was reshaping cities, trains thundered across the countryside, and scientific institutions were flourishing. Yet behind that progress lay growing political tension. As Heisenberg reached his adolescence, the world itself was preparing to fracture. The Great War, the conflict that would later be called World War I, loomed like a dark shadow over Europe. Werner was still in school when the storm broke out in 1914. Too young to fight, yet old enough to witness the devastation, he experienced firsthand the collapse of certainty, both moral and intellectual, that gripped his generation. The old Europe was dying, and in its place a new, uncertain world was being born. For a young mind that already questioned structure and order, these years left a permanent impression. The realization that even the most established systems can crumble. Heisenberg's formal education began at the Maximilians Gymnasium in Munich, where he excelled in mathematics and physics, but also in music and literature. He was not a typical student. He saw patterns in everything: equations, harmonies, the symmetry of words. His teachers noticed a remarkable ability to grasp abstract concepts, though his mind sometimes wandered beyond the curriculum. He preferred solving problems on his own terms rather than following the methods taught. His fascination with numbers was matched only by his love for the piano. Music was not merely a pastime for him, it was a second language. He once remarked that playing Bach's fugues taught him about the hidden structures of order and chaos that exist in both sound and nature. This relationship between precision and emotion, between structure and spontaneity, would later mirror the very principles of quantum mechanics he would help define. In those years, the adolescent Werner also found himself drawn to philosophy. He devoured Plato and Kant. Struggling with the great questions of knowledge, perception, and reality, he pondered how human beings could truly understand the world around them, how the limits of observation shaped what was known. These were not the typical concerns of a teenager, yet they would later become the very heart of his scientific work. For Heisenberg, science and philosophy were not separate domains but twin paths to truth. To understand nature, one had to also understand the mind that observed it. By the time the war ended in 1918, Germany was a nation in ruins, economically shattered and morally exhausted. Yet amid the despair, Heisenberg's intellectual ambition only intensified. As a young man of 17, he joined a nationalist youth movement that emphasized moral renewal and personal discipline, seeking to rebuild the spirit of a broken nation. They met in forests and fields, discussing ethics, self-reliance, and the future of humanity. Though these experiences were partly political, for Heisenberg they also carried a spiritual dimension. A search for clarity and purpose in a chaotic age, this yearning for order and disorder would later echo in his quest to find patterns within the seeming randomness of atomic behavior. In 1920, Heisenberg entered the University of Munich to study physics. His mentor was Arnold Sommerfeld, one of the leading theoretical physicists of the time, and a man who trained an entire generation of scientists who would later dominate 20th century physics. Sommerfeld recognized Heisenberg's extraordinary mathematical talent immediately. His lectures were precise, challenging, and infused with an almost musical sense of logic, qualities that resonated deeply with his young student. Under Sommerfeld's guidance, Heisenberg delved into the emerging field of atomic theory, a frontier filled with promise and paradox. The Bohr model of the atom, proposed only a few years earlier, had already begun to challenge the boundaries of classical mechanics, and Heisenberg was captivated by it. Yet he also sensed its flaws. He intuited that beneath the equations lay something deeper, something not yet captured by existing laws. Heisenberg's early research was marked by both brilliance and boldness. He questioned assumptions that others took for granted. His mathematical intuition allowed him to see through the clutter of theory and focus on essentials, but it was not only intellect that defined him, it was his restless drive to understand. He would spend long hours working on equations, pacing, humming symphonies under his breath, his mind oscillating between the world of music and the world of mathematics. For him, they were reflections of the same cosmic harmony, one expressed through notes, the other through numbers. In 1922, his path led him to Göttingen, the intellectual capital of mathematics and physics at that time. There he encountered Max Born, a man whose influence would be second only to that of Niels Bohr in shaping Heisenberg's future. Göttingen was alive with energy. Lectures by David Hilbert on mathematical logic, discussions on relativity, experiments in quantum radiation. Einstein's theories had shaken the foundations of classical physics, and Planck's concept of quantized energy had opened a door no one could close. Heisenberg walked through that door with the curiosity of a pilgrim entering a temple of knowledge. Under Born's supervision, he explored problems of atomic structure and radiation. His talent for abstraction flourished in this environment, yet he also struggled with the lack of physical intuition that classical mechanics demanded. He could manipulate symbols and equations effortlessly, but visual models of atoms, those neat orbits and shells, did not satisfy him. He wanted to build a physics that did not rely on what could not be observed. During his time in Göttingen, Heisenberg's mind was constantly in motion. He questioned everything, from the nature of electrons to the meaning of measurement itself. He began to suspect that at the atomic level, the very act of observation might change what was being observed. Though he had no proof yet, this seed of thought would later blossom into one of the central principles of quantum theory. But for now, he was still searching for a mathematical language that could describe nature as it truly was, not as human intuition wanted it to be. Heisenberg's life was not without struggle. He suffered from severe hay fever and would often retreat from the city to clear his head. Yet even in moments of illness, his mind refused to rest. He once spent an entire recovery period deriving mathematical relations while confined indoors, describing later how the world of equations seemed more real to him than the physical one outside. His devotion to science was not driven by ambition alone, it was a spiritual pursuit. He saw the laws of nature as reflections of an underlying harmony, a kind of divine order. This belief, inherited from both his philosophical readings and his musical upbringing, gave his scientific work a depth that transcended mere calculation. In 1923, Heisenberg earned his doctorate under Sommerfeld, working on turbulence, a problem so complex that even today it resists complete understanding. His dissertation was not groundbreaking, but it revealed his persistence and analytical depth. He did not shy away from problems that others avoided. That same year, he began corresponding with Niels Bohr in Copenhagen, whose atomic model had become the cornerstone of modern physics. Bohr's philosophical approach, blending intuition, logic, and experiment, fascinated Heisenberg. When Bohr invited him to join his institute in Copenhagen, Heisenberg accepted without hesitation. That journey would mark the true beginning of his transformation from a gifted student into one of the most profound thinkers of the century. The journey to Copenhagen in 1924 was more than a physical relocation. It was a step into a new way of thinking. Bohr's Institute was unlike any other place in the world. It was a hive of debate, collaboration, and imagination. Physicists from across Europe came and went, discussing ideas that bordered on the impossible. In that environment, Heisenberg found his intellectual home. He was in his early 20s, full of energy, his mind sharp and fearless. Under Bohr's mentorship, he learned not only physics but the art of asking the right questions. Bohr pushed him to think not about what electrons are, but what can be said about them, what can be measured, what can be known, and what must remain uncertain. This philosophical precision resonated deeply with Heisenberg's own instincts. Bohr and Heisenberg shared a rare bond. Their conversations often went late into the night, walking along the Copenhagen harbor, discussing the nature of light, matter, and reality. Bohr was the elder sage, methodical and reflective; Heisenberg, the passionate visionary. Together they began to reimagine the atom not as a miniature solar system, but as a dynamic field of possibilities. Every measurement, every experiment seemed to hint at something deeper, a world governed not by certainty but by probabilities. Heisenberg's mind was electrified. He began to see patterns where others saw paradoxes. The mathematics of waves and particles began to blend in his imagination, forming the outline of a new theory, one that could reconcile the contradictions of quantum phenomena. Yet at this stage, Heisenberg was still haunted by one idea: that physics should never rely on what cannot be observed. For him, the invisible paths of electrons around a nucleus were metaphysical fantasies. What mattered were the measurable quantities, the frequencies of light emitted, the energy levels detected, the transitions recorded in experiments. This radical insistence would soon lead him to an entirely new mathematical framework, but before that breakthrough, he had to face frustration and exhaustion. The path to genius is rarely linear, and for Heisenberg it was no exception. The demands of theoretical physics were immense. The problems seemed insurmountable. He worked long hours, often until dawn, driven by an internal fire that refused to dim. By the summer of 1925, worn down by chronic allergies and sleepless nights, Heisenberg sought refuge on the remote North Sea island of Heligoland. There, far from the distractions of university life, surrounded by the crashing waves and open sky, he finally found the solitude he needed. He carried with him nothing but notebooks, papers, and a mind overflowing with unfinished ideas. The sea air cleared his lungs, the silence cleared his thoughts. It was there, in the isolation of that rugged island, that the pieces began to fall into place. He would soon see that the answers he sought were not in visualizing electrons, but in letting go of visualization altogether. The new physics would not be built from images but from relationships, from the interplay of measurable data and mathematical patterns. It was a revelation waiting to be born, a storm gathering in the quiet of his mind. But before that fateful night of insight, before matrix mechanics emerged from the fog of confusion, Heisenberg's life had already prepared him for it. Every note he played on the piano, every philosophical question he pondered, every equation he struggled to balance, all of it was converging toward this singular purpose. The story of Werner Heisenberg is not just the story of a scientist, it is the story of a seeker, a man who chased understanding not for power but for truth. His journey from the classrooms of Munich to the windswept cliffs of Heligoland was a pilgrimage, one that would soon lead him to a discovery that changed the very nature of reality. The island of Heligoland stood like a solitary fortress rising from the gray waters of the North Sea, a place of sharp cliffs and endless horizon. It was there, in the summer of 1925, that Werner Heisenberg retreated in search of peace, but found revolution instead. His hay fever had driven him away from the pollen of mainland Germany, yet it was not his body that truly sought healing, it was his mind. The air was cold and clear, the sea restless, and the nights stretched long into silence. There were no distractions, no colleagues, no debates, only his thoughts, a few papers, and a lamp that flickered in his small room overlooking the ocean. It was here, in this isolation, that Heisenberg began to strip physics down to its barest essence. The tides crashed against the rocks below as if echoing the turmoil of his mind, but slowly, patterns began to emerge out of the noise. For weeks he wrestled with equations that refused to yield. The Bohr model of the atom, though elegant, could not explain why electrons emitted specific frequencies of light, or why certain transitions were forbidden. The old visual models, the neat orbits, the planetary analogies, were breaking apart under the weight of experimental evidence. Heisenberg's frustration grew, but so did his determination. Late one night, surrounded by stacks of notes and the faint hum of the sea breeze, he experienced a moment of extraordinary clarity. He decided to abandon what could not be seen. The orbits of electrons, he realized, were metaphysical ghosts, beautiful but meaningless in the language of true observation. What mattered were only those quantities that could be measured, the spectral lines, the frequencies, the intensities of light emitted during atomic transitions. If the equations of physics were to describe reality, they must describe only what nature allowed to be observed. That decision was the turning point. Working feverishly through the night, Heisenberg began to construct a new mathematical framework, built entirely from observable quantities. He organized data from atomic spectra into arrays, tables of numbers representing possible transitions between energy levels. As he began manipulating these tables, he noticed something strange. The order of multiplication mattered. Swapping the order of operations gave different results, a property unlike anything in classical mathematics. It was a pattern both chaotic and symmetrical, frustrating yet profound. He had stumbled upon what mathematicians called non-commutative algebra, though he did not yet know the term. By morning he realized he had created a new kind of mechanics, one that described not the motion of particles in space, but the relationships between their measurable properties. It was the birth of matrix mechanics, the first complete formulation of quantum mechanics. And it came from a man sitting alone on a windswept island, guided only by intuition, courage, and the relentless desire to understand. When Heisenberg returned to Göttingen and presented his ideas to Max Born, his mentor immediately recognized their significance. Born, with the help of his assistant Pascual Jordan, translated Heisenberg's strange numerical arrays into the formal language of matrices. Together, the three men published their findings, and the world of physics was never the same again. The paper was dense and mathematical, but its implications were seismic. The old, deterministic universe of Newton had collapsed, replaced by a reality governed by probabilities, discontinuities, and uncertainty. For the first time, the atomic world had been given a consistent mathematical description, though it was a world that defied every intuition human beings had built over centuries. In the aftermath of this discovery, Heisenberg's name spread rapidly through the scientific world, yet he remained modest, even uneasy, about what he had unleashed. He understood that his new mechanics was not just a scientific tool, but a philosophical earthquake. The concept of reality itself had to be re-examined. If the equations of physics no longer described objects moving through space, but merely the outcomes of measurements, then what did it mean to say something was real? Was the electron truly there before we looked for it, or did observation itself bring it into being? These were not questions Heisenberg had set out to answer, but they became the inevitable consequence of his discovery. The relationship between the observer and the observed had changed forever. As the debate unfolded, Heisenberg became one of the central figures in a new intellectual movement centered around Niels Bohr's Institute for Theoretical Physics in Copenhagen. The institute became a magnet for young physicists. Dirac, Pauli, Born, Schrödinger, and others, all wrestling with the paradoxes of the quantum world. There were passionate arguments, long walks through the Copenhagen night, and countless cups of coffee as ideas collided and evolved. Bohr and Heisenberg, in particular, formed a partnership that was both collaborative and deeply philosophical. Bohr was slow, deliberate, reflective. Heisenberg was quick, intuitive, and mathematical. Together they created what would become known as the Copenhagen Interpretation of quantum mechanics, the idea that quantum phenomena do not have definite properties until they are observed. Reality, in this view, was not a fixed stage upon which particles acted, but a dynamic interaction between measurement and possibility. The years between 1925 and 1927 were a time of feverish creativity. Theoretical physics seemed to move at the speed of thought. Schrödinger introduced wave mechanics, an alternative formulation of quantum theory that described electrons as waves of probability rather than particles. At first, it appeared to contradict Heisenberg's matrix mechanics, but Heisenberg soon realized that both were different mathematical languages describing the same underlying truth. This synthesis, wave-particle duality, became one of the defining pillars of modern physics. Yet, even as the equations unified, the interpretation divided minds. Einstein could not accept the randomness at the heart of the theory. "God does not play dice," he famously told Heisenberg, to which Heisenberg might have replied, quietly but firmly, that it was not for humans to tell God how to run the universe. It was during this same period, in 1927, that Heisenberg formulated his most famous insight, the uncertainty principle. It emerged naturally from the mathematics of his theory, but carried profound philosophical meaning. The principle stated that it is impossible to know both the exact position and the exact momentum of a particle simultaneously. The more precisely one is measured, the less precisely the other can be known. This was not a flaw of instruments or human imperfection. It was a fundamental property of nature. Reality at the quantum level was not deterministic, but probabilistic. The universe, it seemed, allowed no perfect knowledge. For centuries, science had promised certainty, but Heisenberg's principle revealed that uncertainty was woven into the fabric of existence itself. The world was not built on predictability, but on possibility. The scientific community was stunned. To some, it was liberating. To others, deeply unsettling. Einstein, ever the determinist, challenged Heisenberg's view, proposing thought experiments designed to reveal hidden variables that could restore causality. But each time, the mathematics held firm. The uncertainty principle was not an artifact. It was a law of nature. Bohr defended Heisenberg vigorously, and their joint debates with Einstein became legendary, shaping the philosophical landscape of 20th century science. These exchanges were not mere academic duels. They were dialogues about the nature of reality itself. Could the universe truly exist in a state of indeterminacy until observed? Was observation an act of creation? These questions transcended physics, touching the deepest layers of human thought. As Heisenberg's fame grew, so did his responsibilities. In 1932, at just 31 years old, he received the Nobel Prize in Physics for the creation of quantum mechanics. The citation recognized not only his individual brilliance, but the birth of a new era. When he stepped onto the stage to accept the award, he stood as a representative of a generation that had dismantled the classical worldview and replaced it with something far more mysterious. The applause that filled the hall that day was not merely for a man, but for a transformation in the way humanity understood existence. But history, as always, moved in unpredictable ways. The 1930s brought not only scientific triumph, but political turmoil. The rise of the Nazi regime cast a dark shadow over Germany and over Heisenberg's life. Many of his colleagues, especially those of Jewish heritage, fled the country as the atmosphere grew increasingly oppressive. Heisenberg chose to remain, a decision that would later haunt him. His commitment to science, he believed, should transcend politics. Yet he soon found himself entangled in a moral dilemma that tested his character as deeply as any equation. During the Second World War, Heisenberg became involved in Germany's nuclear research program, leading what was called the Uranium Project. His exact role and intentions remain the subject of debate to this day. Some believe he deliberately slowed progress to prevent Hitler from acquiring a bomb. Others see him as complicit in a misguided effort. The truth, like the quantum world he once described, is uncertain, complex, paradoxical, and unresolved. Despite the controversies, Heisenberg's post-war years were marked by reflection and a renewed dedication to rebuilding German science. He became a central figure in restoring the intellectual and moral fabric of post-war Europe. In his later writings, he turned increasingly toward philosophy, exploring the relationship between science, ethics, and the human spirit. He argued that the discoveries of quantum mechanics demanded a new humility in science, a recognition that our descriptions of nature are not the things themselves, but only the shadows they cast upon the wall of our perception. The reality we can talk about, he once wrote, is never reality itself, but reality as it is understood by the human mind. It was a thought that echoed his lifelong belief that truth lies not in certainty, but in the dance between knowledge and mystery. Through the decades that followed, Heisenberg continued to work and to teach, influencing generations of physicists and philosophers alike. He saw the dawn of the atomic age, the rise of quantum electronics, and the beginnings of the space race. Each new technological triumph carried traces of his early equations: the transistor, the laser, even the foundations of quantum computing. Yet he remained, at heart, a thinker rather than a builder. His interests reached beyond the laboratory into music, theology, and the arts. Friends recalled evenings at his home, filled with piano performances and discussions that moved effortlessly from Bach to Bohr, from mathematics to metaphysics. Heisenberg believed that science without culture was empty, and that the beauty of truth was reflected as much in music as in mathematics. In his later years, he became something of a philosopher of science, exploring the parallels between Eastern mysticism and quantum theory, between Plato's ideal forms and the probabilistic structures of the subatomic world. To him, quantum mechanics was not merely a technical achievement, but a revelation, a window into the subtle interconnectedness of all things. He came to see uncertainty, not as chaos, but as creative freedom. In the ever-changing patterns of particles and waves, he saw the reflection of life itself, dynamic, unpredictable, yet governed by underlying harmony. His words carried a quiet wisdom, born of both triumph and doubt. "Not everything that can be counted counts," he once remarked, "and not everything that counts can be counted." Werner Heisenberg passed away on February 1, 1976. At the age of 74, by then his ideas had become part of the very language of science. The quantum world he had helped reveal had grown into a foundation upon which modern technology and cosmology rest. Yet his legacy was not only in equations, but in perspective. He had taught humanity that knowledge is not the conquest of mystery, but its companion. That the closer we look at reality, the more it recedes into waves of possibility. His life was a journey through the invisible, through the silence between the notes, through the spaces between particles, through the tension between faith and reason. He gave the world not certainty but wonder. Today, when physicists peer into the heart of atoms or search the edges of the cosmos, they still speak the language Heisenberg helped invent. Every experiment, every quantum leap, carries the echo of that lonely night on Heligoland, when a young man dared to abandon the visible and trust in the unseen. His journey reminds us that progress is born not from comfort but from courage, the courage to question, to doubt, to imagine the impossible. In the grand symphony of science, Werner Heisenberg was both composer and conductor, blending mathematics and mystery into a melody that continues to resonate across time. He showed that to understand the universe is not to master it, but to listen to its quiet rhythm, to accept its uncertainty, and to find in that uncertainty the beauty of truth itself. At the turn of the 20th century, the world of science stood at the summit of its confidence. For over 200 years, the laws of Isaac Newton had served as the unshakable pillars of understanding. To the scholars and thinkers of the Victorian age, the universe was a grand machine, predictable, measurable, and obedient to reason. From the movement of planets to the fall of an apple, every motion could be calculated, every force explained. The language of mathematics had conquered nature, and with it came the illusion that there were no mysteries left too deep for human intellect. "The more we know," said the scientists of that golden era, "the more we can control." In the laboratories and observatories of Europe, certainty reigned like a religion. Yet, as the century closed, tiny cracks began to appear in the perfect marble of classical physics, cracks that would soon split open to reveal a new and unsettling truth. The 19th century had been a triumph of precision. Steam engines powered the Industrial Revolution. Railways connected nations. Telegraphs carried messages faster than any messenger could ride, and electricity began to illuminate the world. The universe seemed domesticated, tamed by human intellect. Physicists like James Clerk Maxwell had united electricity, magnetism, and light into a single elegant framework of electromagnetic theory. Thermodynamics had revealed the laws governing heat and energy. Mechanics explained motion, and optics explained vision. It was an age of completion, a time when many believed that the last great problems of physics had already been solved. In 1894, Lord Kelvin, one of Britain's most respected scientists, famously declared that there is nothing new to be discovered in physics now. All that remains is more and more precise measurement. But even as he spoke, two small clouds were forming on the horizon of that bright and ordered sky, clouds that would grow into the storm of the quantum revolution. The first cloud hung over the mystery of light and energy. In laboratories across Europe, scientists were studying the way objects emit radiation when heated, a phenomenon known as blackbody radiation. According to classical physics, as an object grew hotter, it should emit increasing amounts of energy at higher and higher frequencies. Yet experiments showed something impossible. At short wavelengths, the predicted energy shot to infinity. This became known as the ultraviolet catastrophe, a crisis that defied every principle of thermodynamics. For decades, the best minds struggled to resolve it, but every solution collapsed under mathematical contradiction. Then, in 1900, a quiet, cautious physicist named Max Planck proposed an idea so radical that even he doubted it. At first, he suggested that energy was not continuous but came in discrete packets, tiny quanta that could not be divided further. This was not merely a mathematical trick, it was a fundamental shift in the way the universe was understood. Energy, the lifeblood of all motion, did not flow smoothly like a river. It arrived in pulses, like the beats of a drum. Planck's discovery marked the beginning of the end for classical physics, though few realized it at the time. To most scientists, it was a curiosity, an ad hoc solution to a technical problem, but in those small, indivisible packets of energy lay the seeds of a revolution. Planck himself was reluctant to accept the philosophical consequences of his work. He still believed in a continuous deterministic universe, yet the numbers did not lie. Reality itself seemed to be made not of smooth curves but of jumps and steps. The old equations that had once seemed eternal began to tremble. The second cloud appeared a few years later, when Albert Einstein turned his attention to a puzzle known as the photoelectric effect. Experiments had shown that when light struck a metal surface, it could eject electrons from it. Classical wave theory predicted that the brightness of light should determine how much energy the electrons carried. But that wasn't what experiments revealed. Instead, it was the color, or frequency, of the light that mattered. Bright but low-frequency light could not free a single electron, while faint, high-frequency light could knock them loose instantly. The result was impossible to explain if light were merely a wave. Einstein proposed a daring idea. What if light itself was made up of individual quanta, particles of energy later called photons? By suggesting that light behaved as both a wave and a particle, Einstein shattered the comfortable simplicity of the classical world. It was a paradox, an impossibility, and yet it worked. The equations matched perfectly with observation. With these two discoveries, Planck's quantization of energy and Einstein's light quanta, the smooth clockwork universe began to unravel. For centuries, scientists had believed that reality was continuous and predictable, that cause led to effect with mechanical precision. But now, nature seemed to whisper a different story, one filled with discontinuities and probabilities. The deeper physicists looked into the structure of matter. The stranger the landscape became. Electrons, those mysterious carriers of charge, refused to behave like tiny planets orbiting the nucleus. Instead, they flickered between states, existing neither here nor there, defying the rules of motion that Newton had written. The atom, once imagined as a miniature solar system, turned out to be a realm of uncertainty. By the early 1910s, the foundations of physics were beginning to quake. Ernest Rutherford's experiments had revealed that most of the atom was empty space, with almost all its mass concentrated in a tiny central nucleus. His discovery explained the scattering of alpha particles but introduced new riddles. If electrons orbited the nucleus as classical mechanics suggested, they should constantly radiate energy and spiral inward, collapsing into the nucleus in a fraction of a second. Yet atoms clearly did not collapse. Matter was stable. Why? What force prevented this disaster? The old equations had no answer. The classical model of the atom, so neat, so mechanical, had failed. It was Niels Bohr who took the next bold step. In 1913, building upon Planck's and Rutherford's ideas, Bohr proposed a new model of the atom. He suggested that electrons could occupy only certain fixed orbits, each associated with a specific energy level. When an electron jumped between levels, it absorbed or emitted a quantum of light with a frequency corresponding exactly to that energy difference. Bohr's model beautifully explained the spectral lines of hydrogen, the mysterious patterns of light emitted by excited atoms. For the first time, theory matched experiment. Yet Bohr's theory came at a price. It required abandoning the continuous logic of classical mechanics. Electrons did not move smoothly from one orbit to another. They jumped instantaneously and without passing through intermediate states. The idea was revolutionary, almost mystical. Even Bohr admitted that it defied visualization. But it worked. Still, the crisis deepened. Bohr's model, though successful for hydrogen, failed for more complex atoms. Physicists were left with fragments of theories that worked in isolation but could not be unified. Some treated light as a wave, others as a particle. Some described atoms using energy levels, others through statistical patterns. There was no single law that could bind these fragments into a coherent whole. The world that Newton and Maxwell had made sense of now seemed to slip through human comprehension. As the 1920s dawned, physics found itself in a state of existential confusion. The old faith in determinism was crumbling, replaced by questions that seemed almost philosophical. What is an electron? What is a wave? Is light matter, or is matter light? Could the universe itself be built on uncertainty? In the midst of this turmoil, the character of science itself began to change. The confident tone of Victorian certainty gave way to a new kind of humility, one born of bewilderment. Laboratories became arenas of paradox, where experiments produced results that defied common sense. The double-slit experiment, first performed with light, revealed interference patterns that could only be explained if each photon somehow passed through two slits at once. Later, when electrons were used, the same result appeared. Matter itself behaved like a wave. The very notion of what it meant for something to exist began to blur. Was an electron a particle, a wave, both, neither? The questions multiplied, and with them, the unease. Physicists found themselves staring into a mirror that reflected not clarity but contradiction. By 1924, Louis de Broglie, a French aristocrat turned physicist, added another twist to the story. He proposed that if light could behave as both a wave and a particle, perhaps matter could too. Electrons, he argued, should possess a wavelength determined by their momentum. It was an audacious hypothesis, one that no experiment had yet confirmed. But within a few years it would be proven true. The boundaries between matter and energy, once so solid, were dissolving into a shimmering continuum of dualities. The neat categories of classical physics, wave and particle, energy and matter, determinism and chance, were collapsing into ambiguity. The intellectual atmosphere of the time was both exhilarating and disorienting. Across Europe, from Berlin to Copenhagen, from Zurich to Cambridge, young physicists gathered in cafes and institutes, arguing late into the night. They spoke of paradoxes and probabilities, of hidden variables and quantum jumps. The air was thick with ideas that bordered on madness, yet behind the confusion lay the birth of something extraordinary. Out of this chaos, a new language of nature was beginning to take shape, a language that would soon be spoken fluently by a young man named Werner Heisenberg. The scientific crisis of classical physics was more than a failure of equations. It was a crisis of worldview. For centuries, humans had believed that the universe was a grand clockwork, set in motion by divine precision. Every cause had an effect. Every event could, in principle, be predicted if one knew all the forces at play. This was the dream of Laplace, who imagined a supreme intellect capable of calculating the future from the present. But the discoveries of Planck, Einstein, Bohr, and others shattered that dream. The universe was no longer a machine, it was a mystery, one that revealed itself only through probabilities. The deeper scientists looked, the less certain they became. Even time and space, once thought immutable, had been bent and stretched by Einstein's theory of relativity. The firm ground of classical certainty had become quicksand. As the old order collapsed, a new generation of physicists, brilliant, restless, and unafraid, stepped forward to rebuild. Among them were names that would soon become legends: Schrödinger, Born, Dirac, Pauli, and Heisenberg. They inherited not stability, but turmoil. They entered a world where the very meaning of reality was up for debate. Their task was not to polish the old theories, but to invent a new one, to create a physics that could describe a universe built not of certainties, but of possibilities. And in the heart of that quest, Werner Heisenberg would emerge as one of its most daring architects. But before his breakthrough on Heligoland, before the birth of quantum mechanics as a coherent theory, the scientific world had to first confront its own limitations. To accept that knowledge itself might have boundaries. By the mid-1920s, physics stood on the edge of revolution. The equations of Newton and Maxwell still described the visible world perfectly, but in the realm of the very small, the realm of atoms and electrons, they failed utterly. Something new was required, something that could reconcile the discontinuous nature of quanta with the continuous fabric of space and time. The crisis had reached its peak, and the old certainties had been swept away. The next step would not come from experiment alone, but from imagination, an act of mathematical and philosophical courage. It was in this crucible of confusion and creativity that the young Heisenberg, standing on the shoulders of the giants who came before him, would forge a new understanding of the universe, one that would change the course of science forever. By the middle of the 1920s, the confidence that had once surrounded classical physics had melted into uncertainty. What had begun as two small clouds on the horizon had become a storm that swept across every laboratory in Europe. The old faith that the universe could be understood through cause and effect was breaking apart. It was as if nature itself had turned trickster, revealing truths only to snatch them away again. Each new discovery seemed to open more questions than it answered. Beneath the calm surface of equations, chaos whispered. And yet, within that chaos, something remarkable was taking shape. A new kind of order, invisible but profound, waiting for the right mind to see it. The crisis was not simply technical, it was philosophical. The more precisely scientists tried to observe the microscopic world, the more it defied description. Instruments could measure energy and motion, but they could not say what an electron was. Was it a tiny particle darting through space, or a smeared-out wave vibrating in a field of possibilities? When they tried to imagine it one way, the other half of its nature vanished. The experiments did not lie. They simply refused to fit into any picture that made sense. For the first time, physicists had to accept that imagination itself might be the barrier to truth. They needed a new language, one stripped of imagery, rooted only in relationships and numbers. The frustration of the age can still be felt in the writings of its scientists. Letters exchanged between Bohr and Einstein read like the correspondence of philosophers struggling with faith. Einstein pleaded for a universe governed by reason, a cosmos in which God did not play dice. Bohr, with quiet persistence, answered that it was not for mankind to dictate how the universe must behave, it was only for us to describe what we can observe. Their dialogue became the moral heartbeat of modern physics, the struggle between determinism and uncertainty, between the desire for control and the humility of acceptance. Meanwhile, experiments grew stranger. In Cambridge, J.J. Thomson's cathode ray tubes showed electrons bending through magnetic fields like invisible threads of lightning. In America, Millikan's oil drop experiment measured the charge of those same electrons with impossible precision, confirming their existence but deepening the mystery of their nature. Each result pointed to the same conclusion. The microscopic world followed rules unlike anything in the macroscopic one. The atoms that built steel and stone, air and water, obeyed a logic alien to everyday intuition. The universe was no longer one story told at different scales, it was a collection of stories told in different languages. In the cafes of Munich and the lecture halls of Göttingen, young physicists debated what this meant. Some clung to the old ways, convinced that hidden variables must exist, unseen mechanisms waiting to be discovered that would restore order. Others, more daring, began to suspect that the disorder was real, that the randomness in nature was not ignorance but essence. They spoke in whispers of a new kind of physics, one that would describe probabilities instead of certainties, but to many this seemed like surrender, an abandonment of science itself. For centuries, the goal of physics had been to predict. Now it seemed the best it could do was to estimate. The crisis was existential. What did it mean to know something if knowledge could never be complete? At the center of this turmoil stood Niels Bohr in Copenhagen, his institute a sanctuary for restless minds. It was there that a generation of physicists gathered, drawn not by comfort but by curiosity. They came with their contradictions, their theories half-formed, their equations trembling between success and failure. Bohr listened to them all, his pipe glowing softly in the evenings as discussions filled the rooms. He spoke slowly, weighing each word as if it carried the gravity of the universe itself. To Bohr, the goal was not to restore the old order, but to build a new one from the fragments. Every great and deep difficulty, he would say, bears in itself its own solution. It forces us to change our thinking in order to find it. Change was coming. The year 1924 brought Louis de Broglie's daring hypothesis that matter could behave like light, that electrons, those supposed particles, possessed wavelengths and frequencies. His idea unified the two great clouds that had haunted physics, the quantization of energy and the dual nature of light. But the equations were incomplete, the language too new. Physicists needed a system, a structure, a mathematical framework that could hold all these paradoxes without collapsing. That framework was still hidden, waiting to be uncovered by someone capable of seeing beyond appearances. In universities across Europe, chalk dust filled the air as blackboards overflowed with half-finished equations. Schrödinger in Zurich began to imagine waves that lived not in space, but in abstract configuration space. Max Born in Göttingen searched for mathematical clarity amid confusion. Pauli, sharp and skeptical, tore apart every theory that could not withstand logic. Each of them sensed that something extraordinary was within reach, but none could yet grasp its form. It was as if they were standing before a great tapestry, each seeing only a few threads, unable to perceive the design that connected them. The crisis deepened into wonder. Experiments grew ever more precise, and each one contradicted the last. When beams of electrons were fired through two narrow slits, they created interference patterns. Not lines like bullets, but ripples like waves. Yet when detectors were placed to observe which slit each electron passed through, the pattern vanished. Observation changed the outcome. Nature seemed to know when it was being watched. This single experiment, simple yet profound, revealed the heart of the new mystery. The act of measurement was not passive, it was participatory. The observer was no longer separate from the observed. Such results demanded courage to interpret, and courage was what the young generation had in abundance. They had grown up amid the wreckage of war, the fall of empires, the collapse of certainties in politics and philosophy alike. Theirs was a world already acquainted with uncertainty. It was no coincidence that the revolution in physics came from those who had lived through revolution in life. They understood that order could emerge from chaos, that truth might lie not in permanence but in change. By 1925, the sense of crisis reached its climax. Classical mechanics could no longer explain the stability of atoms, the emission of light, or the structure of matter. Even the great Einstein admitted that he did not know where to turn next. New foundations must be found, he wrote, but we do not yet know what they are. The mood was one of both despair and exhilaration, the feeling that the edge of knowledge had been reached, and that beyond it lay something vast and undiscovered. It was in this atmosphere that Werner Heisenberg, still in his early 20s, began to find his voice. The turbulence of his times matched the turbulence of his thoughts. To him, the crisis of physics was not a failure but an invitation, a call to strip away assumptions and rebuild from what could be known. He rejected the notion of imagining electrons as miniature planets, or waves moving through invisible ether. Instead, he believed physics should concern itself only with what could be observed, the frequencies of light, the energies of transitions, the measurable outcomes of experiments. The rest, he said, was metaphysics. It was a bold stance, one that cut through the fog of speculation with surgical precision. Heisenberg's insistence on observable quantities became the philosophical foundation for the new quantum mechanics. It was not born in comfort, but in crisis, a response to decades of contradictions. The very impossibility of reconciling the old laws forced him to think differently. When he withdrew to the island of Heligoland, escaping his hay fever and the noise of academic debate, he carried the entire crisis of classical physics with him. It was there, in the solitude of that rocky island, that the centuries-old edifice of Newtonian certainty finally gave way to something entirely new. But even before his breakthrough, the shape of the revolution was visible. The equations of classical physics had relied on the notion that every physical system could be described by its position and momentum at any given time. With those two quantities, one could, in theory, predict the entire future. Quantum phenomena shattered that ideal. The more precisely physicists tried to determine an electron's position, the less precisely they could know its momentum. The concept of a perfect prediction was gone. Nature had imposed a limit, not on instruments, but on knowledge itself. This was not merely a mathematical inconvenience, it was a philosophical earthquake. The universe was no longer a clockwork machine grinding predictably toward a preordained future. It was a symphony of probabilities, each note played not with certainty but with chance. Determinism, the faith of Newton and Laplace, had died, and in its place rose a world both terrifying and beautiful, a world alive with possibility. For the scientists who lived through it, the crisis of classical physics was a rite of passage. It demanded that they abandon the comfort of clarity and embrace the ambiguity of truth. It taught them that knowledge is not the conquest of mystery, but its conversation, and it revealed that beneath the surface of chaos lies a deeper order, one that cannot be seen, but can be felt in the rhythm of equations, in the pulse of probability, in the whisper of the atom. By the time Heisenberg completed his revolutionary work in 1925, the old world of physics was gone forever. In its place stood a new vision of reality, one in which energy came in quanta, particles behaved like waves, and observation itself shaped existence. The crisis that had begun with Planck's uneasy equation and Einstein's photon had ended in transformation. The language of science had evolved, and with it, the human understanding of the universe. Yet the echoes of that crisis never truly faded. Every generation of scientists since has inherited its questions. What is reality? Does it exist independently of observation? Are the laws of nature deterministic or probabilistic? Each attempt to answer those questions leads back to the dawn of quantum mechanics, to the moment when certainty gave way to wonder. Looking back, it is clear that the crisis of classical physics was not a collapse but a birth, the painful, luminous birth of modern science. It forced humanity to confront its limits, and in doing so to expand them. It revealed that even in uncertainty there is structure, even in randomness there is rhythm. The atom, once thought to be the end of divisibility, became a gateway to infinite complexity. The universe, once seen as a predictable clock, became a living poem written in the language of probability, and in the midst of it all, standing between two worlds, the old of precision and the new of uncertainty, was Werner Heisenberg, the quiet mathematician who dared to trust the unseen. His story, and the story of the crisis that made him, remind us that progress is born not from certainty but from doubt. The end of one truth is always the beginning of another. The crisis of classical physics was the universe's way of whispering that the human mind had outgrown its cage. And when that cage broke, light escaped. Not the steady light of reason alone, but the shimmering, unpredictable light of discovery that still dances in every laboratory, every equation, every dream of understanding the world as it truly is. In the summer of 1925, the North Sea lay cold and restless, its surface reflecting a pale, endless sky. On a small, wind-beaten island known as Heligoland, a young physicist named Werner Heisenberg stepped off a ferry and into history. He was only 23 years old, frail in appearance but aflame with thought. His health had driven him here, chronic hay fever that tormented him every spring. Yet destiny had another reason. The isolation of Heligoland, far from the pollen and noise of continental Europe, offered him something medicine could not: silence. And in that silence the universe was waiting to speak. The island itself was a curious place, a rugged red cliff rising from the sea, dotted with fishermen's cottages and gulls circling in the wind. There were no distractions, no lectures, no politics, only the sound of waves striking stone and the distant hum of ships. Heisenberg rented a small room in a guest house overlooking the harbor. The walls were bare, the furniture simple, but for him it was enough. He brought with him stacks of papers, notebooks filled with unfinished equations, and the restlessness of a man standing at the edge of discovery. Each morning he would walk along the cliffs, letting the sea air clear his lungs, and each night he would return to his desk, determined to solve a mystery that had haunted physics for decades. The mystery was the atom, the invisible core of all matter, the stage upon which light and energy performed their strange dance. Classical physics had failed to describe its behavior. Bohr's atomic model had been a temporary scaffold, explaining the hydrogen spectrum but collapsing under the weight of complexity. Schrödinger's wave ideas were still unformed. Dirac had not yet emerged. The entire field of quantum theory was a maze without a map. Heisenberg, however, had a unique gift. He thought not in pictures but in principles. Where others saw orbits and particles, he saw relationships and transitions. He wanted a physics that would describe only what could be observed, not the invisible paths of electrons, not the imagined trajectories of particles, but the measurable facts of experiment. As the days passed on Heligoland, Heisenberg began to strip away the unnecessary scaffolding of physics. The more he simplified, the clearer his vision became. He realized that the equations of classical mechanics were built upon assumptions that no longer held true at the atomic scale. Position and momentum, the twin pillars of Newtonian description, could not be known simultaneously for an electron in orbit. The very concept of a path, of a definite trajectory through space, was meaningless. What could be observed, however, were the frequencies of light emitted when an atom changed state, the spectral lines that appeared when electrons leapt from one energy level to another. These transitions were measurable, repeatable, and real. Heisenberg decided to build his theory entirely from them. Each night, under the faint glow of a lamp, he filled page after page with calculations. His handwriting was small and deliberate, his thoughts racing faster than his pen could follow. The sound of the sea outside became a rhythm that matched the rhythm of his reasoning. He worked not from textbooks, but from intuition, letting mathematics guide him where imagery could not. The key, he began to suspect, lay in organizing these measurable quantities, the intensities and frequencies of radiation, into a kind of mathematical table, where each entry represented a possible transition between energy states. It was a radical idea, one that abandoned centuries of visualization in favor of pure abstraction. Late one evening, after hours of relentless calculation, he noticed something extraordinary. When he multiplied these tables of quantities in different orders, the results were not the same. Unlike ordinary numbers, where 2x3 equals 3x2, his new quantities refused to obey commutation. Their multiplication depended on order. This violation of mathematical convention might have seemed like an error, but to Heisenberg it was a revelation. The non-commutative nature of his quantities mirrored the very behavior of the quantum world, a world where the sequence of measurements changed the outcome. He had found, in the language of mathematics, a reflection of nature's own paradox. He did not yet know it, but he had discovered the foundation of matrix mechanics, the first complete formulation of quantum mechanics. Without using the term matrix, a word borrowed later by Max Born, Heisenberg had created an entirely new kind of mathematics, one that described the physical world not through trajectories but through transitions. The atom, in his theory, was no longer a miniature solar system but a dynamic system of relationships, governed by the probabilities of change rather than the certainties of motion. It was an idea so revolutionary that even Heisenberg struggled to believe it. Exhausted, he stepped out into the cold night air. The island was silent except for the wind and the waves. Above him, the stars shimmered. Distant fires scattered across the infinite dark. For centuries, those stars had symbolized order, the grand geometry of the cosmos. But now, looking up, Heisenberg saw them differently. The universe was not a fixed clockwork, but a living, vibrating field of possibilities. The certainty that had once comforted science was gone, replaced by something more mysterious and beautiful. The realization that reality itself was built from uncertainty. The sea murmured below, and Heisenberg stood there, his mind illuminated not by starlight but by understanding. When morning came, he felt a clarity he had never known before. He spent the next several days formalizing his calculations, translating intuition into equations. He worked without pause, sometimes forgetting to eat, driven by the thrill of discovery. The numbers began to fall into place. He could now describe how electrons emitted or absorbed energy, not by imagining their motion, but by computing the transitions between states. Every experimental observation, every spectral line measured in laboratories from Berlin to Copenhagen, could be predicted by his equations. The success was staggering. After a week of feverish work, he wrote to his mentor Niels Bohr, explaining his new approach. The letter, though modest in tone, carried within it the seed of a revolution. Bohr was intrigued but cautious. The mathematics was unfamiliar, the interpretation unsettling. Yet he sensed that Heisenberg had touched something profound. When Heisenberg returned to Göttingen, he showed his notes to Max Born, who immediately recognized the structure of matrices in the strange tables of quantities. Born and his assistant, Pascual Jordan, helped refine the mathematics, and together the three published a paper that would change the course of physics forever. The paper was dense, technical, and unlike anything that had come before. It described a world where observable quantities replaced invisible mechanisms, where the atom was defined not by where its particles were, but by what could be measured of them. The reaction was immediate and polarizing. Some physicists saw genius, others saw madness. Schrödinger, still working on his own wave equations, dismissed the matrix formulation as obscure and repugnant. Einstein admired the courage but doubted the implications. Even Bohr struggled to interpret what it meant, but there was no denying its power. The predictions matched experiments with uncanny accuracy. The riddles of atomic spectra, the unexplained irregularities that had haunted physics for decades, were suddenly resolved. What had seemed impossible was now calculable. The revolution had begun. For Heisenberg, the days following his discovery were filled with both exhilaration and unease. He had built a framework that worked, but its meaning eluded him. What was this strange mathematics describing? Was it a new reality or merely a new way of calculating? He wrote in his diary that he felt as though he were standing before a mysterious gate, beyond which lay an entirely new world of thought. The gate was open, but he did not yet know what lay beyond. He sensed, however, that he had crossed a boundary that could never be uncrossed. The brilliance of his insight lay not only in its mathematics, but in its philosophy. Heisenberg had redefined what it meant to know something in science. No longer could one speak of electrons as having definite positions or paths. Instead, one could speak only of the probabilities of their behavior. The act of measurement, the very process of observation, had become part of reality itself. This was a radical departure from the objective universe of Newton and Maxwell, where the observer was separate from the observed. In Heisenberg's world, the two were entwined, a single, inseparable system. The observer's choice of measurement affected what was observed, and thus, in a profound sense, reality itself was participatory. In the months that followed, as his paper spread through the scientific community, Heisenberg became both famous and misunderstood. Many struggled to grasp his abstract approach. They longed for pictures, for something they could imagine. But Heisenberg resisted. He insisted that the human mind, limited by classical intuition, could not visualize the quantum world. It could only describe it mathematically. This insistence on abandoning visualization was perhaps his most courageous act, an act of intellectual faith. To him, truth did not require imagery, it required consistency. The goal of science, he once said, is not to discover how nature looks, but how nature acts. Meanwhile, the rest of Europe was still reeling from the aftermath of the First World War. Nations were rebuilding, economies staggering, ideologies clashing. In that turbulent landscape, the young physicists of the 1920s formed their own kind of rebellion, not against governments, but against the old order of knowledge. They gathered in seminar rooms and cafes, sketching equations on napkins, arguing late into the night about the meaning of reality. To them, Heisenberg's discovery was not just a theory, it was liberation. It proved that science could survive the death of certainty, that truth could exist even without clarity. On Heligoland, the physical act of isolation had become the metaphor for intellectual isolation. Alone on that island, surrounded by sea and silence, Heisenberg had been forced to rely entirely on his own reasoning. There were no mentors to guide him, no experiments to check his intuition, only thought that solitude had stripped him of assumptions and left him face to face with the raw structure of reality. In his later years, he would often reflect on those nights, calling them the most intense moments of my life. It was there that he realized the universe was not mechanical but mathematical, not visible but relational. And from that realization emerged one of the greatest revolutions in human understanding. The breakthrough on Heligoland was not merely a scientific event, it was a transformation of thought. It marked the end of the age of certainty and the birth of the age of probability. It showed that knowledge could emerge from confusion, that truth could arise from doubt. Heisenberg had dared to look beyond the horizon of the visible and had found order where others saw chaos. His discovery would soon give rise to an entirely new world, a world of quantum mechanics where energy, matter, and observation danced together in patterns both unpredictable and precise. And yet, for all its abstraction, his work was grounded in the simplest of principles, that science must describe only what can be known. From that humility came one of the boldest leaps in intellectual history. Alone on an island, armed with only a pencil, paper, and an unrelenting mind, Werner Heisenberg had changed the very language of the universe. When Werner Heisenberg left Heligoland and returned to the mainland, he carried with him not just a notebook full of numbers, but a new conception of reality. The sea air that had once burned his lungs now felt like the breath of revelation. He boarded the ferry to Hamburg in silence, the waves rising and falling beneath him, like the equations still turning in his mind. In those few days of isolation, the rules of the universe had changed, and he alone knew it. He had gone to the island to escape pollen. He returned having rewritten the laws of nature. The train carried him south toward Göttingen, that quiet academic town whose lecture halls had birthed so many revolutions in thought. Heisenberg's heart beat with both excitement and fear. His ideas were fragile, untested, and as yet unnamed. When he stepped into the office of Max Born, the senior physicist who had mentored him, he laid the pages on the desk almost apologetically. Born leafed through them, frowning at the strange symbols. The calculations did not resemble anything known in mechanics or electrodynamics. They were patterns, grids of numbers whose order seemed arbitrary, until Born noticed that their multiplication followed a rule from linear algebra, something he had once taught his students but never imagined could describe reality. These were matrices. What Heisenberg had done without realizing it was to express the behavior of the atom in a new mathematics. Born's eyes widened as he grasped the implication. The old coordinates of classical mechanics, position and velocity, were gone. In their place stood arrays of measurable quantities, transitions, intensities, frequencies. The mathematics did not depict motion through space. It depicted relationships of change. Born called in his assistant Pascual Jordan, a brilliant young mathematician barely older than Heisenberg himself. Together the three men worked through the equations, line by line. For days they filled chalkboards, the air thick with dust and argument. Slowly, the chaotic scribbles resolved into a consistent formalism. It worked The numbers predicted the exact spectral lines of hydrogen and matched experimental data to the last decimal. In July 1925, they published their findings under the modest title on quantum theoretical reinterpretation of kinematic and mechanical relations. The title gave no hint that it marked the end of the classical era. The paper announced a new mechanics, one that would soon be known as matrix mechanics, and it left the scientific world reeling. For 2 centuries, physics had described motion as the trajectory of particles through space. Now Heisenberg's equations describe not particles but the probabilities of transitions between energy states. Reality had become a tapestry woven from possibilities. At first the reaction was confusion. Even Heisenberg confessed that he could not visualize what his own mathematics meant. The equations worked, but they described a world that could not be imagined. There were no orbits, no forces in the classical sense. Only patterns of change. To many physicists, it felt as if the ground had vanished beneath their feet. Schrödinger, still developing his own wave theory, accused Heisenberg of abandoning physical intuition. A theory that cannot be visualized, he said, is not physics. But others saw something deeper. Pauli, ever the skeptic, declared the work a miracle of clarity. Bohr wrote to Heisenberg, urging him to visit Copenhagen and discuss its meaning. The revolution had begun to gather its disciples. When Heisenberg arrived in Copenhagen later that year, Bohr welcomed him like a son. The institute buzzed with excitement. Young physicists from every corner of Europe crowded into its narrow rooms, their blackboards overflowing with equations that stretched the imagination. In those smoke-filled evenings, ideas clashed and fused like atoms in collision. Bohr paced the floor, gesturing with his pipe, speaking in long, winding sentences that forced his listeners to think rather than simply hear. Heisenberg sat quietly, absorbing everything. He was still uncertain of what his mathematics truly meant, but Bohr pushed him to look beyond the numbers. "What can we say about nature?" Bohr would ask, pausing after every phrase, not what it is, but what we can say about it. It was in these conversations that the philosophical heart of quantum mechanics began to form. The new physics did not describe things as they are, but as they behave when observed. The act of observation had become inseparable from the outcome. To measure was to participate. Reality itself, at the smallest scale, seemed to exist not as a fixed structure, but as a set of potentialities that crystallized only when observed. This was not a universe of certainty, it was a universe of becoming. The collaboration between Bohr and Heisenberg grew intense. They walked for hours along the Copenhagen harbor, their debates echoing across the water. Bohr, older and cautious, emphasized complementarity, the idea that wave and particle descriptions were not contradictory but complementary aspects of a single truth. Heisenberg, younger and bolder, focused on mathematical consistency and experimental verification. Together, they forged the Copenhagen Interpretation, the understanding that the quantum world does not possess definite properties until measured, and that physics can speak only of what can be observed. Back in Göttingen, Bohr and Jordan continued to refine the mathematics. Their work introduced formal rules for the non-commuting quantities that had first puzzled Heisenberg. Out of these relations would later emerge Heisenberg's most famous equation. Deltax and deltap greater than or equal to h, 4pi, the uncertainty principle. But that was still 2 years away. In 1925, the immediate triumph was the success of matrix mechanics itself. Its predictions were precise, its logic unassailable. The spectral patterns that had mystified experimentalists for decades could now be calculated with mathematical elegance. Across Europe, the news spread rapidly. In Zurich, Erwin Schrödinger studied Heisenberg's paper, and inspired by de Broglie's idea of matter waves, began to develop his own alternative formulation. Within months he produced the wave equation that now bears his name. When applied to the hydrogen atom, Schrödinger's equation produced exactly the same energy levels as Heisenberg's matrix mechanics. 2 utterly different pictures, one visual and continuous, the other abstract and discrete, leading to identical results. The realization astonished everyone. Quantum theory, it seemed, was larger than any single interpretation. Einstein, watching from Berlin, admired the mathematical beauty but doubted its philosophical implications. Heisenberg's theory violated his deepest conviction, that the universe obeys deterministic laws. God does not play dice, Einstein said. Heisenberg respected him immensely but could not agree. The data were undeniable. Nature did play dice, or rather it played a deeper game whose rules included chance. As months turned into years, the young physicist found himself at the center of a storm. Conferences in Como, Solvay, and Copenhagen became battlefields of the mind. The greats of science, Einstein, Planck, de Broglie, Born, Bohr, Schrödinger, Pauli, gathered to debate the meaning of the new quantum world. In the famous Solvay Conference of 1927, Einstein launched his paradoxes. Bohr and Heisenberg answered each in turn, their arguments fierce but respectful. The discussions lasted late into the night, and by morning, even Einstein admitted he could find no flaw in their reasoning. The universe, it seemed, had spoken through equations stranger than imagination. For Heisenberg, those years were a blur of discovery and exhaustion. He traveled constantly, lecturing, collaborating, refining his ideas. His work with Bohr deepened into friendship, though their debates were endless. Heisenberg's health remained fragile. Long bouts of fever and insomnia punctuated his triumphs. Yet he pressed on, driven by something larger than ambition, a sense of wonder, a desire to understand the architecture of existence itself. In 1927, while working again in Copenhagen, he found the missing piece. The non-commutative mathematics of matrix mechanics implied a fundamental limit to knowledge. No matter how perfect the measurement, one could never know both the position and the momentum of a particle with infinite precision. The very structure of the equations forbade it. This was not a technical limitation, but a law of nature. Heisenberg realized that uncertainty was not a flaw in observation, but an intrinsic property of reality. It meant that the universe was fundamentally indeterminate at its core. He published the result under the humble title On the Perceptual Content of Quantum Theoretical Kinematics and Mechanics. And with it, the modern understanding of the quantum world was born. The uncertainty principle shocked even those who had already accepted matrix mechanics. It stripped away the last vestiges of classical determinism. The future could no longer be predicted with certainty, only with probability. Every measurement disturbed the system it sought to describe. Every act of observation reshaped the observed. In the words of one contemporary, Heisenberg has built the mathematics of doubt. Yet it was not doubt in truth, but doubt in perfection. The acknowledgement that knowledge has boundaries. Within those boundaries, however, lay infinite depth. In 1932, the Nobel Committee awarded Heisenberg the prize in physics for the creation of quantum mechanics. When he stood in Stockholm to receive the medal, he spoke quietly about the journey that had begun on a lonely island 7 years earlier. He thanked Planck for opening the door, Bohr for guiding his thought, and Born for giving structure to his mathematics. But he said little about himself. To him, the discovery had not been personal triumph, but revelation, a moment when nature allowed humanity to glimpse a hidden order. Heisenberg's breakthrough did not end with physics. It changed philosophy, chemistry, even art. The certainty that had guided the 19th century gave way to a new sensibility, one that accepted ambiguity as truth. The modern world of probability, statistics, and complexity was born from the mathematics he had scrawled on Heligoland. The transistor, the laser, the quantum computer, all traced their lineage to that moment when Heisenberg multiplied tables of numbers and found the universe looking back through them. Years later, reflecting on that time, he wrote that he had felt as if the ground beneath me had given way, leaving me suspended in a new kind of space where only relationships mattered. That sense of suspension, of floating between certainty and mystery, defined his entire life. He continued to explore the implications of quantum theory, extending it to nuclear physics and cosmic phenomena. But he never lost the humility that the equations had taught him. The closer he looked at reality, the more he saw that it could not be captured in words or images, only in mathematics, and even then, only partially. The island of Heligoland still stands, battered by the sea, its cliffs scarred by time. Visitors who walk its paths today see only wind and water, not the silent battle that once took place there. the battle between old thought and new, yet in that solitude, a young man had faced the infinite and returned with a new map of existence. The discovery he made there would ripple outward for generations, reshaping how humanity perceives itself and the universe. Heisenberg's breakthrough was not the end of the story but the beginning of a new language for understanding creation. It taught scientists that the world cannot be described by certainty alone, that truth comes not from control but from connection. It revealed that at the smallest scales, reality is not a collection of things but a web of relationships, vibrations, probabilities, patterns of interaction. The observer and the observed are parts of the same dance. Looking back across a century, one can see how the revolution of 1925 transformed more than physics. It altered the human spirit. It replaced arrogance with awe, precision with participation. It showed that even when the visible fails, the invisible can still speak through reason, and it all began with a frail young man on a remote island, listening to the sea and daring to ask how nature behaves when no one is watching. The world that emerged from Heligoland was one of paradox and beauty, uncertainty and unity. The classical age had ended, but a new kind of order had been born, an order not of predictability, but of possibility. Heisenberg's equations became the heartbeat of the quantum age, and their rhythm still echoes in every atom, every beam of light, every digital signal that carries human thought across the planet. As the waves break eternally against the cliffs of Heligoland, they carry with them the memory of that night when the universe changed. In the spray and the wind, one can almost hear the whisper of mathematics turning into meaning, of thought becoming truth. Werner Heisenberg had found what every seeker of knowledge hopes to find, not certainty, but understanding, not control, but communion. The world would never be the same again. In the years that followed, Heisenberg's lonely breakthrough on Heligoland, the strange mathematical framework he had created began to take shape into a coherent and powerful new system, and matrix mechanics. The first complete and working form of quantum mechanics, it was a theory unlike any that had come before it, one that abandoned the visual comfort of orbits, forces, and trajectories, and replaced them with the austere precision of numbers arranged in infinite arrays. These matrices, at first nothing more than mathematical curiosities, became the language through which the subatomic world could finally be described. In the hands of Heisenberg, Max Born, and Pascual Jordan, the equations began to sing with meaning. They showed that atoms did not move as miniature planets around a sun, but existed as patterns of possible transitions, leaping from one state to another in discrete jumps. It was as though nature herself spoke in flashes, each quantum a syllable of light, each transition a word in the sentence of creation. The beauty of matrix mechanics lay in its audacity. It did not attempt to explain how electrons moved or why they behaved as they did. It simply described what could be observed. The frequencies and intensities of light emitted or absorbed by atoms. The rest, the invisible motion between those observations, was stripped away. In doing so, Heisenberg had cut physics free from centuries of assumption. The atom was no longer something that could be pictured, but something that could only be calculated. The equations themselves became reality. They obeyed a strange rule. The order in which they were multiplied mattered. This property, called non-commutation, reflected the new logic of the quantum world, a world in which the sequence of measurements changed the outcome, in which the act of observation was not neutral but transformative. Born and Jordan gave this mathematics a formal structure, showing that Heisenberg's quantities were indeed matrices, and that their non-commuting nature could explain the limits of knowledge at the smallest scales. From their collaboration emerged a new law, that certain pairs of physical quantities, such as position and momentum, could never be known with arbitrary precision at the same time. This was not a failure of measurement, but a feature of reality. Out of the very heart of matrix mechanics grew the principle of uncertainty, the realization that nature itself forbids complete determinism. The equations told scientists that the more precisely one measured where an electron was, the less precisely one could know how fast it was moving. The universe had rules, but those rules allowed only probabilities, not certainties. Matrix mechanics was not easy to understand, even for physicists. Its abstraction frightened some and fascinated others. There were no clear pictures to hold on to, only mathematical relationships that seemed to defy visualization. Schrödinger would soon propose his wave mechanics, a more intuitive description that pictured electrons as waves of probability rather than discrete jumps. But when the two theories were compared, they proved to be mathematically equivalent, two different windows onto the same unseen world. The unity of these views marked a profound moment in science. Reality, it seemed, could be expressed in many forms, yet remain one. The impact of matrix mechanics rippled across the landscape of thought. For centuries, science had sought to reveal the hidden machinery of nature, to find the gears and levers behind the world's motions. Heisenberg's equations showed that there were no gears, no hidden levers, only relationships, only interactions. The universe was not a machine but a symphony of probabilities. It was governed not by strict causation, but by patterns of potential. To predict the future was now to speak in terms of likelihood, not inevitability. And yet, far from weakening science, this humility made it stronger. The predictions of matrix mechanics matched experiment with astonishing accuracy. The once mysterious spectra of atoms were explained perfectly. Quantum mechanics, born from Heisenberg's radical logic, became the most precise and successful theory in the history of physics, but its implications reached far beyond the laboratory. Matrix mechanics changed humanity's conception of reality itself. It erased the boundary between observer and observed, reminding scientists that to measure was to participate, that knowledge and nature are entangled. It taught that the universe at its core is not a collection of objects but a web of relationships, each defined by its connection to the whole. In the shimmering arrays of numbers, Heisenberg had uncovered the architecture of uncertainty, the structure of mystery itself. From the static equations of classical physics emerged a world alive with motion and possibility, a world where chance and law coexist in delicate balance. In the years that followed, the matrix formalism became the foundation for everything from nuclear physics to chemistry, from lasers to transistors, from quantum computing to cosmology. It redefined not only what scientists could calculate, but what they could believe. The neat, clockwork universe of Newton was gone. In its place stood a universe of shimmering probabilities, where certainty dissolved but understanding deepened. And through it all, the equations of matrix mechanics endured, silent, exact, and timeless, like the music of the cosmos written in mathematical form. Heisenberg's creation was more than a theory. It was a philosophical awakening. It proved that reality does not owe us simplicity, that nature reveals herself not through what can be seen, but through what can be known. And from that revelation came the recognition that even in uncertainty there is order, even in mystery there is truth. The matrices, once scrawled by a young man on an island far from the world, had become the language of existence itself. In 1927, 2 years after his discovery on Heligoland, Werner Heisenberg introduced an idea that would shake not only the foundations of physics but the very meaning of knowledge itself. It was called the uncertainty principle. Though to Heisenberg, it was less a principle than a revelation, a whisper from nature about the limits of what could be known. For centuries, science had been built upon the belief that if one could measure all the forces and positions in the universe, one could predict the future with perfect precision. This was the dream of Newton and Laplace, the faith of an age that saw the cosmos as a great clock. But Heisenberg's equations told a different story, a story in which certainty dissolved and knowledge itself became bounded by the laws of existence. The uncertainty principle emerged naturally from the mathematics of quantum mechanics. When Heisenberg examined his non-commuting matrices, those strange arrays where the order of multiplication changed the result, he realized that they carried a message about reality. Certain quantities, like the position and momentum of a particle, were not just difficult to measure together, they were fundamentally incompatible. The more precisely one knew where a particle was, the less precisely one could know how fast or in which direction it was moving. The act of measuring one property unavoidably disturbed the other. At first, Heisenberg thought it might be an experimental limitation, a flaw of instruments or human clumsiness. But soon he saw that it was no accident. The uncertainty was woven into the fabric of nature itself. This realization changed everything. The universe, it seemed, did not operate like a machine ticking with predictable rhythm. Instead, it behaved like a symphony of possibilities, each note dependent on how it was heard. At the atomic level, objects had no fixed existence until they were observed. They existed only as probabilities, as waves of potential outcomes. Observation did not reveal reality, it created it. Heisenberg's insight was more than mathematical, it was philosophical. It declared that the observer and the observed were entangled in a single act of creation. Knowledge was no longer a mirror of nature, but a part of it. The line between subject and object, between measurement and truth, had blurred. When Heisenberg first shared his discovery with Niels Bohr in Copenhagen, the two men debated for days. Bohr, with his deep sense of philosophical balance, saw in it a confirmation of his idea of complementarity, that wave and particle, certainty and uncertainty, are not opposites but partners in describing reality. Einstein, however, resisted fiercely. God does not play dice, he said, unable to accept a universe ruled by probability. But Bohr answered, with calm conviction, it is not for us to tell God how to play. Between those two sentences, Einstein's defiance and Bohr's acceptance, stood Heisenberg, quietly aware that the truth was beyond either comfort or control. The uncertainty principle became the cornerstone of modern physics. It was not merely a statement about measurement, but about existence. It meant that there are boundaries to knowledge, not imposed by ignorance, but by nature herself. The deeper one looks into the world, the more one realizes that there is no ultimate precision, no final map that captures reality completely. Every act of observation changes what is observed. Every attempt to pin down nature's secrets alters them. The atom, the light, the electron, all exist in a realm where certainty is impossible but meaning is abundant. Philosophers, too, felt the tremor. The idea that truth itself could be uncertain resonated far beyond laboratories. It echoed in art, literature, and human thought. The tidy world of absolutes began to dissolve into a world of relationships and interpretations. In painting, abstraction replaced realism. In music, atonality replaced harmony, the very spirit of the 20th century. Its questioning, its fragmentation, its search for meaning in chaos, seemed to mirror the uncertainty Heisenberg had revealed in nature. Yet Heisenberg never saw uncertainty as chaos. To him, it was a form of order, a subtler, deeper law that preserved balance in the universe. Just as one cannot hear both the melody and the harmony of a symphony in perfect isolation, one cannot know both the position and the momentum of a particle. Nature hides some truths so that others can exist. In this balance lay the beauty of creation. Heisenberg once said that the more he studied quantum mechanics, the more he felt a spiritual awe, as though he were glimpsing the edge of divine logic. Practically, the uncertainty principle defined the behavior of everything small and vast, from the stability of atoms to the fusion of stars. Without uncertainty, electrons would collapse into nuclei, and matter itself would cease to exist. The very structure of the universe depends on this delicate indeterminacy. What appeared as limitation turned out to be the source of stability, the reason the world can exist at all. As Heisenberg's insight spread, it changed not just how scientists calculated, but how humanity perceived its place in the cosmos. Certainty had been the foundation of power. Now humility became the foundation of understanding. Science could still describe nature with astonishing accuracy, but it could no longer claim to predict everything. Knowledge became participatory, dynamic, alive. In the quantum world, truth was not a destination, but a conversation. Between mind and matter, between question and answer. Heisenberg's uncertainty principle remains one of the most profound and poetic discoveries in all of science. It stands as a reminder that even in a universe governed by mathematics, mystery endures. It tells us that to know is not to possess, but to witness, that the closer we approach the essence of things, the more they shimmer between being and becoming. It is not an admission of failure, but an invitation to wonder, an open door into a reality that forever dances just beyond the reach of certainty. In the years that followed his discovery, Werner Heisenberg's ideas intertwined with those of his mentor and friend, Niels Bohr, giving birth to one of the most influential interpretations of quantum mechanics, the Copenhagen Interpretation. It was not a single statement or formula, but a philosophy, a way of understanding the strange, new reality revealed by quantum theory. The world had entered an age where the old language of cause and effect no longer sufficed, and where the act of observation itself had become a creative force. Together, Bohr and Heisenberg sought to make sense of this new world, not by taming it, but by learning to see its paradoxes as truths. Their collaboration was both scientific and deeply human. Bohr, older and contemplative, believed that every great discovery required humility before nature. Heisenberg, young and mathematically gifted, was a man of fierce logic and intuition. Where Bohr spoke in philosophical riddles, Heisenberg spoke in equations, but beneath their differences was a shared purpose: to bridge the gap between what can be observed and what can be said. In long discussions that stretched late into the night at Bohr's home in Copenhagen, they walked the narrow line between science and metaphysics. They knew that quantum mechanics had not just rewritten physics. It had changed the relationship between humanity and the universe. The essence of the Copenhagen Interpretation lay in a simple but revolutionary idea: that the quantum world does not possess definite properties until it is observed. Before measurement, particles exist in a superposition of states, waves of probability that represent all possible outcomes. The act of observation collapses that wave, forcing the system to choose a single reality. In this view, the observer is not a passive witness but an active participant in the unfolding of events. The universe is not merely out there, independent of perception, it is shaped by the very act of perceiving. Bohr called this principle complementarity, the notion that reality can appear in mutually exclusive ways depending on how it is observed, as a wave or a particle, as certain or uncertain. Yet both descriptions are necessary for a full understanding of truth. This idea defied common sense. It contradicted centuries of scientific philosophy that treated the observer as separate from the observed, the experimenter as neutral. Einstein objected passionately, insisting that reality must exist independently of observation. "Do you really believe," he once asked Bohr, "that the moon is not there when no one looks at it?" Bohr, with his quiet conviction, replied, "It is wrong to think that the task of physics is to find out how nature is. Physics concerns what we can say about nature." For Bohr and Heisenberg, the new science was not about uncovering an objective universe, but about describing the relationship between our questions and nature's answers. Their interpretation was not meant to mystify but to clarify. It acknowledged the limits of human knowledge and embraced them as part of the structure of reality. In the quantum realm, certainty was an illusion, probability was the rule. Yet within that uncertainty lay a profound order, a harmony that could be expressed in mathematical form. Heisenberg's equations and Bohr's philosophy were two sides of the same coin. Together they revealed a universe that is both rational and mysterious, governed by laws yet open to chance. The Copenhagen Interpretation became the foundation of modern quantum mechanics, shaping generations of physicists who followed. It provided a framework for understanding experiments that defied classical explanation, from the behavior of electrons to the interference patterns of light. It guided the development of atomic energy, semiconductors, and quantum computing. But beyond its scientific achievements, it transformed the way humanity understood reality. The universe was no longer a detached mechanism, it was a dialogue, a dynamic interplay between the observer and the observed. Bohr and Heisenberg's partnership, however, was not without tension. Their debates were intense, often bordering on the personal. Bohr's philosophical patience sometimes clashed with Heisenberg's precision, yet it was in this friction that brilliance was born. Each challenged the other to think deeper, to look beyond equations or words and see the essence of truth. Their friendship survived wars, political turmoil, and the weight of history. When they walked together along the Copenhagen harbor, discussing the mysteries of light and matter, it was as if they were listening to the heartbeat of the universe itself. The philosophical implications of their work extended far beyond science. The idea that reality depends on observation resonated with thinkers, artists, and theologians alike. It suggested that meaning is not fixed but relational, that truth arises from interaction. In art, this became a metaphor for perspective, in philosophy, for consciousness, in spirituality, for participation in creation. The Copenhagen Interpretation dissolved the illusion of separateness, revealing a world woven together by the act of awareness. To many, this was unsettling, the loss of an objective universe, the end of certainty. But to Heisenberg, it was liberating. He saw in it a new harmony between science and philosophy, between mind and matter. The laws of physics were not cold and mechanical, they were intimate, reflective, alive. In one of his later writings he said, "What we observe is not nature itself, but nature exposed to our method of questioning." In those words lies the heart of his legacy, the understanding that knowledge is a relationship, not a possession. The Copenhagen Interpretation stands today as one of the most profound achievements of human thought. It reminds us that the universe is not something to be conquered, but something to be understood, through dialogue, respect, and wonder. It teaches that truth is not static but unfolding, and that our search for meaning is part of the very process that gives the universe form. Through the collaboration of Bohr and Heisenberg, science learned to see itself not as a detached observer, but as a participant in the mystery of existence, a realization as beautiful as it is humbling, echoing the eternal dance between knowing and being. Werner Heisenberg's legacy extends far beyond the equations he wrote or the theories he proposed. His work reshaped not only physics, but the very philosophy of knowledge, and his influence continues to echo through every branch of modern science and technology. By the time he reached the later decades of his life, the once young physicist from Würzburg had become a symbol of the new age, an age in which humanity had learned that uncertainty was not weakness, but wisdom. The quantum revolution he helped ignite had changed the way people looked at the universe, and with it, the way they looked at themselves. It had revealed that reality was not a fixed stage upon which life unfolded, but a living web of possibilities. To understand the world, one had to accept that knowing and being are forever intertwined. Heisenberg's contribution was more than a discovery, it was a transformation of human thought. His mathematics had opened doors to technologies that would shape the modern era: semiconductors, lasers, nuclear energy, and the foundations of quantum computing. Yet Heisenberg himself remained a philosopher at heart, concerned not just with how the universe works, but with what it means to know it. He believed that science, at its core, was a moral and spiritual endeavor, a way to approach truth with reverence. In his later writings, he reflected that the greatest lesson of quantum mechanics was humility. "We have to remember," he said, "that what we observe is not nature itself, but nature exposed to our method of questioning." The act of observation was not dominance but dialogue, not conquest but communion. After World War II, Heisenberg found himself at the center of moral scrutiny. During the war, he had led Germany's uranium project, a scientific effort that raised difficult questions about responsibility and ethics. Whether he deliberately slowed progress to prevent the creation of a nuclear weapon or simply followed his duty as a scientist remains debated to this day. But what is certain is that the war changed him. In its aftermath, Heisenberg dedicated himself to rebuilding science as a force for peace. He became a leading voice for international cooperation, urging nations to see that the power revealed by atomic research must serve humanity, not destroy it. He saw in quantum physics a lesson for society, that all things are connected, that isolation and certainty are illusions, and that understanding requires participation. In the post-war years, Heisenberg turned increasingly toward the philosophical implications of his work. He spoke often of the parallels between modern physics and ancient philosophy, between quantum uncertainty and the mysteries pondered by Plato, Aristotle, and even Eastern thinkers. He saw quantum theory as a bridge between the rational and the mystical, a language that united science and spirituality. The more he studied nature, the more he felt that reality could not be captured by logic alone. There was always something beyond measurement, an essence, a wholeness, a harmony that science could touch but never possess. In his mind, quantum mechanics was not the end of explanation, but the beginning of understanding. The legacy of Heisenberg's ideas reached far beyond physics laboratories. The concept of uncertainty found echoes in psychology, economics, art, and philosophy. It became a metaphor for the modern condition, a recognition that knowledge is always partial, that truth must be approached with openness and courage. In literature and art, the deterministic world of the 19th century gave way to abstraction, ambiguity, and depth. The same spirit that animated Cubism, modernism, and existential philosophy flowed from the same realization, that reality is not fixed but interpreted. Heisenberg had shown that the observer changes what is observed, and this principle resonated deeply with artists and thinkers seeking to understand human perception and meaning. Even in the world of technology, the shadow of his equation stretches across time. The quantum principles he helped define are the foundation of the digital world, the behavior of electrons in transistors, the operation of lasers, the principles behind superconductivity and quantum entanglement. All of these trace their lineage back to Heisenberg's insight that matter is governed not by certainty, but by probability. Today, as scientists develop quantum computers capable of processing information in ways once thought impossible, they continue to walk the path he began. Every qubit, every algorithm rooted in quantum superposition, is a living echo of the mathematics born on Heligoland a century ago. But perhaps Heisenberg's greatest legacy lies in his vision of science as a human enterprise. He never saw physics as a mere collection of laws, but as a conversation between humanity and the universe. He believed that the role of the scientist was not to dominate nature, but to listen to it, to find harmony between human understanding and cosmic truth. In this way, Heisenberg stood at the meeting point of two traditions, the analytical rigor of the West and the contemplative insight of the East. His view of the quantum world resembled the wisdom of ancient mystics, who taught that reality is interconnected, that the observer and the observed are one, and that knowledge is participation in the unfolding of being. In his later life, Heisenberg continued to teach and write, his lectures filled with both technical precision and quiet poetry. He spoke not only of physics, but of responsibility, creativity, and wonder. He saw science as a moral act, one that demanded honesty and humility. When asked what the quantum revolution meant for humanity, he replied that it reminded us of our limits, but also of our place within the grand design. We are part of the pattern we seek to understand, he said. In knowing the universe, we come to know ourselves. These words captured the spirit of a man who had gazed into the heart of matter and found not chaos but connection. Werner Heisenberg died in 1976, but his ideas remain alive in every laboratory, every philosophical debate, every moment when humanity dares to question the nature of reality. His work continues to shape how we see the cosmos, not as a clock, but as a chorus of possibilities. Through his mathematics, the invisible became knowable, and through his philosophy, knowledge became humble. The legacy of Heisenberg is the legacy of quantum thought itself. That uncertainty is not the enemy of truth, but its companion, that the boundaries of knowledge are not walls but horizons, and that, in the shifting patterns of the unseen, there lies a deeper order, one that invites us endlessly to explore.